Okay, today we would like to discuss about the introduction to the IC technologies. It is the continuation for the last class. Uh, so we have stopped here of discussing in the last class at this point, whatever the existing IC technologies are there. Okay, so different IC technologies are available. But anyway, one important point that we have to remember is that how do we evaluate, how do we understand? So what is the, how do we characterize an IC technology? It's an important one. Okay, so how do we characterize an IC? So different parameters we need to consider. Based on that one, we can say that the IC technology will be better or good performer or low performer. Okay, so for that one, first important point is that the power consumption. So power consumption of an IC is very, very important. Okay, so why the power consumption is important? Generally, uh, generally we are nowadays people are using the portable devices, right? So what do you mean by the power consumed by the circuit? Which means that the circuit has to take the power information, power from the power supplies, right? So it has to take the energy from the power supply and it utilizes it within the circuit. While it is utilizing that power, it generates some kind of heat. Okay, so therefore, from the power supply to circuit, power supply to the circuit, so it has to draw some amount of the current, some amount of the power from the power supply. Okay, so therefore, the circuit is identified whether it is a low power device or the low power circuit or maybe high power circuit, how much amount of the power it is consumed or taken from the power supply. Okay, so it must be very low volt, low power it has to take from the power supply. That's what we have to keep in mind. Such a way that we have to generate the circuit, we have to create it, or we have to design the circuit. Okay, once whenever the power is taken from the power supply, so it activates the available transistors existed in the circuit, right? So therefore, when it is switching, one transistor is switching from on to off. There are so many number of transistors are there in the IC. Each and every transistor will be on and off depending upon the input signal that you apply. While it is on and off, how much amount of the power it is taking, right? So that is also the power we need to consider for that. Okay, so therefore the totally how much amount of the power it is taken from the power supply and how much amount of the power is utilized within the power supply, within the circuit itself. Okay, so therefore that is the power consumption that we have to consider. Suppose if the power is consumed by the circuit is very, very high, for example, that means the switching on and off will take a more amount of the power it is taking, for example. So this point, how the transistor is consuming the power when it is switching on and off. So we will see that point later on. But just remember that if you want to make the transistors on from on off to on, certain amount of the power will be consumed. Okay, what is the power? What is that power? All these things we'll see later on. So this power is very, very important factor. So if the power consumed by the circuit is very high, the automatically heat will be generated. So the heat will be generated. So since we are talking about millions of the transistors on a single small silicon chip, so even if it is to consume a nanowatt of power also, so billions of the transistors will be more and more power will be consumed. Okay, that means more and more heat will be generated. So that is not acceptable. So that is not acceptable in portable devices. So whenever we are using the portable device, nowadays mobile phones that we are using. So just a second. Okay, the heat will be generated. So the portable for a portable devices consideration, the heat must be very, very low. Okay, otherwise we are not able to use our mobile phones. But whenever you are using the mobile phone, it is heating. Nobody interested on that one. So therefore, for portable concepts, okay, and one more thing is that battery operated systems that we are using in the portable devices. So therefore, power drawn from the battery as well as the utilization of the power also must be low. So that will affect the heat generated by the circuit. Okay, so therefore, low power consumed circuits are essential for our IC design. Okay, so that is one thing that we have to characterize. The next one is propagation delay. Propagation delay. So therefore, the delay of the IC is also very important. Normally, the delay is defined by as soon as you are applying the input signal, how fast the circuit is activated. Okay, so that is decided with the delay of the circuit. So nowadays we are using the 4G mobiles and 5G mobiles. The operator thus with the delay of the circuit is very small. Okay, so therefore we have to try to attempt the circuit for the low delay circuits. Okay, I have removed, no problem. So the propagation delay of the circuit is an important information. Similarly, the area offered by the circuit also, area. That means once we design the circuit, we have to convert it into a layout. Okay, so how much area it is taking in a given small, how much area, whether it is a certain, when compared to the previous one, it should occupy very less area. Okay, this is the one parameter we have to consider. Next, another one is very important one is cost is also an important one. If you want to make an integrated circuit, how much cost is there in this one also. Okay, and reliability. So how reliable the circuit, the integrated circuit is. So all these parameters are characterizing an integrated circuit. Okay, so for example, if you consider the most importantly, normally if you consider generally the power consumption and the propagation delay is only the consideration in this course we normally do. Okay, the area and cost, reliability issues, interconnections, and everything we are not going to consider in this course. But most of the cases, whenever we are designing a circuit, we focus mainly on power consumption and delay. How much, how less power consumed by the circuit, whatever the design of the circuit is there, how best way we can reduce the power consumption, how best way to reduce the delay of the circuit. Okay, is it clear? So in that sense, just different technologies are available. So these technologies are compared with the power consumption and the propagation delay. Okay, generally there is a trade-off is existed between the power consumption and the delay. If the power consumption is less, the delay will be increases. If the delay is less, if the delay is less, power consumption will be increases. So there is a trade-off between the power consumption and the delay. These points are also we look at when coming to the classes. Okay, so an IC technology means, so whatever the IC that we are considering, what is the active element that we are considering? Active element. Active element is generally a transistor. Okay, this is generally a transistor. So depending upon the type of the transistor, we say the name of the technology. This is the one way of identifying the IC technology. Okay, for example, if I say that bipolar junction transistors, BJT, so then the BJT IC technology, okay, IC technology, BJT IC. Or if you're using the MOS transistors, for example, okay, MOSFETs. This is a MOS technology. So normally people will call it as a BJT technology. This is called MOS technology. And sometimes we come with the CMOS technology. Of course, the MOS consisting of different flavors are there. Metal oxide field effect transistor has a field effect transistors has 3 flavors are there. One is NMOS technology, NMOS, PMOS, and CMOS. So if you're using the NMOS technology, if you're using the PMOS technology, if you're using the CMOS technology. Okay, and the later the MOS technology can be specified in that way. Okay, so I'm removing that point and I'm considering in this way only. Okay. The next one is BiCMOS technology. So this is another important technology that people have invented. So just they have taken the advantage of the bipolar junction transistors and CMOS together, an IC consisting of both the bipolar junction transistors at one side, BJT is at one side, CMOS is another side. So therefore, they will consider both NMOS and BJT and CMOS. That is called BiCMOS technology, right? So therefore, this is the technology. Next one is gallium arsenide technology. There is another technology is there, gallium arsenide technology. So these are the fundamental technologies that are available. Of course, as I mentioned the previously, carbon nanotube technology is also there. FinFET technology is also there. Tunnel FET technology is also there. So these are the FinFET and the tunnel FET technology is nowadays the people are trying to realize the circuits, but they are trying to give the best counterpart for the compared to the bipolar junction transistor as it is in CMOS. Okay, so this is the current research is in FinFET technology and the tunnel FETs. But don't think that the CMOS is obsolete. Okay, CMOS is also is in running because it has a distinct advantage when compared to any other technologies. Okay, so let us consider this small discussion related to the comparison between the among the different technologies based on the power consumption and propagation delay. So as I mentioned, that ECL is emitter coupled logic is actually BJT related technology. Say BJT related technology. Similarly, if you consider this MOS, this is a MOS related technology. It is a MOS related. It is a BJT related technology. This is also MOS related technology. So this is actually the combination of both MOS technology, BJT, and MOS technology, both combined together. It is other than the silicon. Okay, so it is other than silicon technology. So you can understand that either BJT or MOS or BJT combination of MOS altogether is a silicon-based technologies. So this bipolar junction transistor, MOSFET, BiCMOS. All these things are, we can call it as silicon-based technologies. Silicon-based. And that means the silicon is the basic material to construct an integrated circuit. Right? So whereas gallium arsenide is not the silicon-based one, it is other than the silicon material we use. Gallium is one material, arsenic is another material. We have to use a different material. It's not a silicon. Okay. So now we observe carefully in this particular slide. That's very, very important one. So when we talk about the power consumption, initially people have realized the bipolar junction transistors. Okay, so after vacuum tubes, people have invented a bipolar junction transistor. Okay, so therefore BJT is the most popular element to construct ICs. Okay, so therefore one of the important technology in BJT is ECL, emitter coupled logic. So whenever they are realizing the circuits or integrated circuit with the help of ECL, okay, they found that the power consumption of the circuit is very, very high. So as you see from x-axis from 0 to towards the 100 milliwatt, okay, you can see the power consumption at the nearest to the end point. We can say that the high power is there. That's what we observe. Okay, so for example, for the clarity, I'll write in this way. So these are 4 parts, for example. Okay, so can you suggest me what is this part belongs to? What is this part belongs to? So this part belongs to that. It says that you can imagine, you can say something like this very easily. It is a low power, low delay, less delay. Okay, just a second. Low power. Okay, and low delay. Can we say that this region, something like that? Yeah, fine. Next, what about the thing here? Here is a high delay, low power. Sorry, high power. I'm sorry, high power. No, here it's not low power, it's a high power, right? I'm extremely sorry. This is high power. Power is high during this region. So the first quadrant here, it's low power, as well as low delay. What about here? Low power, high delay. Are you agree with me? This kind of differentiation. So yeah. So when we consider this particular diagram, so we can combine this entire diagram into 4 quadrants. So this four quadrants. The first quadrant is a low power and low delay. Above that one, we can see the low power and high delay. Adjacent to that one, high delay and high power, and the last one at the bottom of the right corner, high power and low delay. Okay, so it is self-explanatory that if you are using the bipolar junction transistor, it is observed that it is consumes the high power but low delay. Okay, fine. When we talk about the NMOS technology, later they feel that people will feel that okay, the power consumption of the circuit is very high, because high power circuits are not at all acceptable to realize the integrated circuit in portable applications. Okay, in fact, so the number of transistors on an IC will limit the power consumption of the circuit. Okay, we are not able to provide more number of devices IC. It is not possible to do that one because power consumed by the circuit is very high. Okay, so later they come with the NMOS technology. In fact, they first realized the CMOS technology, then they came to the PMOS and they came to the NMOS. But okay, for the simplicity, I'm writing that NMOS technology first. Okay, so in this NMOS technology, what they have done, they have realized the ICs with the help of NMOS transistors. MOS technology they have used. Okay, see here what they have observed that it is normal. Obviously, it is somewhat the power is medium. I can say that medium power can be there, but the delay of the circuit is very high. Okay, so that is what it is observed that. Later, the people have realized the ICs with the help of CMOS devices. Later, they realized the CMOS devices. Therefore, the problem is that the power should be power consumption of the circuit is very high, right? Now the power consumption is changed to the low power consumed device if you're using the CMOS technology. Okay, therefore the CMOS is very popular because it consumes less power compared to the other technologies, bipolar junction transistor technology or NMOS technology. So why the CMOS offers less power consumption? This also we investigate in the coming classes. Okay, but we observe that the one parameter is very good. That means the power consumption of the circuit is very low. The CMOS technology, but the delay of the circuit is increases. Should not. So there is a cause. There is a trade-off between the power and delay. Whenever we are trying for the low power devices, we need to sacrifice for the delay. Whenever we are releasing for the high speed, the power will be this kind of approach, right? So therefore, the people say that okay, why can't we use? Why we are using the silicon, even though it is an abundantly available and cheapest cost when compared to the other materials. Let us try for another material other than silicon. So they come with the gallium arsenide technology. So they come with gallium arsenide technology. It's a completely different material. Gallium arsenide is both are different materials. Okay, so with this particular gallium arsenide technology, they are able to get a low power as well as low delay. observed from the diagram also. It is possible with the gallium arsenide. But the later point of time, they realized that, so the cost of making ICs with gallium arsenide is very, very high. Okay, so more amount of the cost of the system is the cost of the IC is very, very high. Okay, so therefore gallium arsenide manufacturing cost or material formation cost is high. Cost is very high for the gallium arsenide, whereas the silicon-based ICs are very cheap when compared to the gallium arsenide. There is a huge differences there between the gallium and arsenide. For example, I'm telling that $1 is used for silicon-based ICs, for example, maybe $100 is used for gallium arsenide. So there is that much differences there, cost differences there between this particular thing. So whenever the street is called gallium arsenide, that is a BiCMOS technology. So BiCMOS technology they have used. So the center part. So you can see there is a the minimum thing that can be achieved by using the bipolar junction transistors. Okay, so what is the basic advantage of using this BiCMOS? So what exactly the information is in it? So let us see here in this way. So generally, normally you see if you consider the BJT, sorry. So the BJT is, as I mentioned, that the power is very low actually. So the power consumption is very high, but we can say that the speed of the circuit is good. Speed is good, right? That's what we observed from the diagram. The delay means only the speed only, right? Now, whereas if you consider the MOS technology, CMOS technology, what is the good here? Power. Power is good. So low power is there, right? So therefore, why can't we combine these things? So because of this low power, so what is the advantage of using this low power? So the advantage of this low power is it allows us, okay, okay, so when we consider about the CMOS technology, it is allows us more number of transistors can be accommodated in given area. More transistors can be accommodated in the given area, chip area. Okay, that's what we can do. So whenever we have a low power devices are there, it is possible more number of transistors can be accommodated in a given small area. Whereas the power consumption is high, it is not possible to provide all the things, all the transistors in the given area. Okay, but we found that what is the biggest problem with this CMOS technology? Of course, first instant of the time that we can say that the delay is high. Okay, so what is the problem with this one? Power is high. So therefore, what I can do is that if I consider any integrated circuit, first the functionality of the circuit is realized with the help of CMOS. Okay, that means, so for example, a full adder, if we consider minimum number of transistors for this one is, so that means maximum number of transistors are 28 transistors. Okay, so therefore, by using the CMOS technology, I can realize that functionality. But whereas in order to increase the driving capability or the speed of the circuit, I'll use the bipolar junction transistors at each and every corners of the IC. So therefore, in order to increase the driving capability, that place I have to use the bipolar junction transistors. For implementation of the circuit, I use the CMOS. So that is what the bipolar junction transistor BiCMOS technology is all together. Okay, so therefore, taking the advantage of bipolar junction transistor, taking the advantage of CMOS and combine them, and it will be considered as BiCMOS technology. Clear? So therefore, the BiCMOS technology is will provide you the moderate power consumption and moderate propagation delay. Clear? That's what we can say. Now that is all about the technologies, ICs technologies. Nowadays, the people are using, starting from the bipolar junction transistor to the tunnel FETs. Okay, we are not going to talk about FinFETs and tunnel FETs related power consumption and related information. This is not out of the scope of this syllabus. So, but if you are interested, just to compare, understand these concepts related to the FinFETs and tunnel FETs. Now, so as I mentioned that whatever may be the technology it is, it doesn't matter. Okay. So what is the starting material we have to consider, right? So as we know that silicon is a semiconducting materials are used for integrated circuits. Okay, we are going to use semiconducting materials. So not conductors, not insulators. As everybody knows that materials are classified into, broadly classified into three types: conductors, semiconductors, and insulators. So for making an electronic circuits, that too an integrated circuits, we use semiconductors. Okay. So the semiconductor means the different materials are also there. One important material is silicon. Silicon semiconductor we have to use. Carbon is there, arsenic is there, boron is there. So many things are there, right? So out of all those things, we use the silicon is the semiconducting material we have to use for integrated circuits. If you want to make an ICs, the most of the cases, majority of the ICs are ICs based on silicon only. Okay. So why the silicon is preferred? That's important question. Okay. So if you observe in the periodic table for the semiconductors, okay, the fourth group elements are the semiconductors in the periodic table. First one is the carbon, last one is germanium. Okay, so middle one is silicon. So semiconductor materials, if you're using, why can't we use the carbon? So the carbon has a high thermal stability. That means if you want to make, if you make any integrated circuit with the help of carbon, it can withstand high temperatures. Okay, so the operating temperature of the carbon is very, very high. But biggest problem with this one is energy gap is also very high. Energy gap is very high. So if energy gap is very high means more potential that we have to apply in order to make that carbon atoms are active or conductive, we can say that. So therefore, since the energy gap is very high, even though the thermal stability is good for the carbon, we don't prefer the semiconductor carbon as a semiconducting material for the integrated circuits. Okay. So therefore, but if you consider that germanium, if you consider the germanium, the energy gap is low. Okay, that point is we focus on energy gap, but energy gap is low. But the thermal stability is very less. But here it is another problem is that operating temperature for the gallium ICs are very, very low. So therefore, we have to consider the silicon for for moderate values for the energy gap as well as thermal stability. So compared to the between these two semiconducting materials, right? So therefore, the silicon is moderate energy gap and thermally stable compared to the carbon and germanium. This is the one aspect why the silicon is used for the integrated circuits. Another important one is, very, very important one is, it's a great affinity to oxygen. So this is what actually driving force for the silicon to use in IC manufacturing. Okay, so that means whenever we have a silicon, it is automatically forms silicon dioxide, SiO2, when you place the silicon in oxygen chamber. Okay, if you place a silicon in oxygen chamber on oxygen, it is when it is exposed to the oxygen, silicon dioxide is formed. So silicon dioxide is an insulating material. That kind of insulating property is necessary for integrated circuits. So generally, if you want to make an insulating material on a silicon substrate or silicon material, an extra material that we have to use. Okay, but it's very simple that if you want to form a silicon dioxide insulating material that is required for IC fabrication, we can easily form silicon dioxide just placing the silicon dioxide in oxygen chamber. So actually, this is what the driving force why we have to use the silicon semiconductor in IC fabrication. Okay, so therefore it is based on electrical property based thing, and this is for manufacturing based property. Okay, so therefore because of these two essential requirements, essential considerations, silicon material, silicon semiconductor is used for IC fabrication. Clear? Fine. Now, so as I mentioned that a small discussion here on the silicon semiconductor industry or semiconductor industry. That means making an integrated circuits by using the silicon industry. So you can see the graph here. So the global semiconductors, semiconducting market actually. Okay, when compared to the any engineering other fields, this much growth cannot be observed for any other industry. Okay, semiconducting industry is a popular industry and profitable industry compared to any other industries. So that's what it is saying, this graph. So it is always increasing in fashion from 2008 onwards also, this value is increases more and more. Okay, so therefore whenever you want to enter into this semiconducting industry, in manufacturing industry or the R&D work and whatever it may be, you'll find a great opportunities in it. Okay, because it is ever ending technology and industry actually. Okay, so therefore just for I can say that is the size of the market. So it's a billions of dollars market is there for the semiconductor industry. Okay, you can see also this graph. So as I mentioned that ICs can be classified into different types depending upon how many number of devices that we can accommodate in an IC. Okay, just this slide shows that what are the possible devices, application devices can be constructed based on this particular classification of ICs. So, for example, if you consider the silicon small scale integrated circuits, we normally face the logic gates, flip-flops we can realize. If you consider the medium scale integration, so it is possible to realize the counters, multiplexers, adders, something like this. Similarly, depending upon the type of integration, we can design some kind of applications. So in the VLSI, we consider the 30-bit microprocessors they have realized. Of course, nowadays people are using the 64-bit microprocessors. But in the 1980s itself, between 1980 and 1990, people were realized that this kind of integration is possible. That's the reason why they thought that there is the end of the integrated circuit technologies, but it is not like that. So it is go from ultra large scale to giant scale integration. So as I mentioned previously, this integration is possible is because of, as I mentioned, that miniaturization, that means the scaling of the devices. So that means that, as I mentioned previously, so the device dimensions are reduced drastically when the technology advances. Okay, so because of the miniaturization and advancements in the fabrication process lead us to move from a small discrete component to the giant scale integration. You observe that. Okay, so without many advancements in the, so of course it is possible to reduce the component, but if the machinery is not there, for example, to fabricate the device, it's meaningless. Okay, so in addition to the miniaturization, the technology, the manufacturing industry also has to come forward to make that particular integrated circuits of that much small size. Okay, so that's what we have to think about it. So of course, I have mentioned that it's a bipolar junction transistor, BiCMOS, all these things are silicon-based technologies, but gallium arsenide is another technology. Okay, so let us talk about some more detail about the silicon CMOS technology. As I mentioned, that CMOS technology is the most advantageous technology compared to the bipolar junction transistors and NMOS or PMOS alone technologies. Okay, what is the reason? Okay, because of this one, it is possible to create an VLSI circuits cost effective and high performance. Okay, so therefore with this particular technology, CMOS technology, it is possible to realize the high performance circuits and very low price. With a low price, you are getting you are able to realize the VLSI circuits. So that is an advantage of using the BiCMOS, sorry, silicon CMOS technology. In fact, you can imagine if you consider the RISC processors that they have designed. So how high performance can be achieved, something like this. So 35 million instructions per second that particular VLSI circuit can execute. Okay, so these many instructions per second the IC can execute. Okay, so that is the most powerful execution technology is there. That means the silicon technology is there for high performance. Okay, but whenever we are talking about the high performance means, so the silicon technology is the first line come for to do this particular task. Of course, nowadays the beyond the CMOS also is available, but at the point of discussion of 1980s to 1919, that was the very great achievement people have done. It's not joke, 35 millions of instructions per second. But because the scenario is progressing, okay, that means the requirements for the day-to-day life is also increases. So that's the reason why it is also not sufficient the execution speed of this one also. It's more the speed is required sometimes. Okay, so in that situation, we go for BiCMOS technology. Okay, so silicon BiCMOS technology is the most suitable one if you want to move the throughput rate of the instruction number of instructions per second will be more. Okay, so by using this one, by using the BiCMOS technology, 100 million instructions per second can be possible to execute. Okay, so this is because of increasing demand of applications. Nowadays, for example, if you take one mobile phone, okay, some features they will add. So in the next 6 months, they will increase another, they are incorporating another application for that. Okay, that means the number of instructions per second must be increased. Okay, so in that situation, the technological advancements also will play a crucial role. So for example, from the CMOS technology to the BiCMOS technology, we can see almost another 75 million instructions per second are increased, right? So therefore, the silicon MOS technology is BiCMOS is also very dominating technology for IC fabrication. Okay, as I mentioned that what is this BiCMOS means, it's a combination of BJT and CMOS advantages. Okay, nothing more than that. So if you want to go for more and more, okay, so I'm 100 millions per instructions are also not sufficient. Then we have to go for gallium arsenide technology. Okay, so therefore, okay, the technology is not, there is no end point for the technology. If the one technology is not sufficient to do this one, other technology people will invent. Okay, therefore there is a lot of scope is there. So if you are able to introduce a new technology, there will be certainly some growth will be there for that part. Okay, so this is what the initially in the initial days, people, if they have realized the integrated circuit, first SRAM they have realized. So this is an SRAM. So and this is a 404 microprocessor. Okay, so 4 billion transistors and more number of transistors are there. The people will realize it in this particular ICs. So this is a IC. Actually, some millimeter by millimeter area is there in this one. So these many number of transistors that they are able to achieve. Okay, therefore this fabrication processing and how do we fabricate this one, and how do we form the layout for this one? All these things will be there in our syllabus. So we'll, at the end of the course, you will identify that how we can make such kind of devices. Okay. And so therefore, as I mentioned, that the number of transistors are increases, yeah, if the semiconductor industry or IC technology is allow the more number of transistors in a given area, so the processors are changing from 4004 microprocessor to dual core, okay, and quad core, octa core processor also came into existence. It is only because of scalability, because of scaling technology. That means miniaturization of the devices allows more number of transistors in a given small area. So if the more number of devices are there, more functionality can be implemented. Okay, so that's what the scenario will present in this one. Okay, this is only because of if you are accommodating the more number of transistors in a given IC. Okay, so so this is another point is that the clock speed of operating speed. So the clock speed also will drastically increases from this point to this point. Now the people are settled for 3 GHz. So the operating clock frequency, clock speed of any integrated circuit is starting from the 1947 from megahertz to people are settled for 3 GHz operating frequency. Therefore, if you want to measure the processor speed in terms of the clock frequency only, we have to define. But nowadays, people are not interested on using the clock speed to identify or measure the performance of the IC. So people are using the number of cores that are using, whether dual core, octa core, quad core. Okay, so how many number of cores that you are using, that decides the performance of the circuit nowadays. But before that, people were used to use the clock operating frequency. Okay, please remember that point. So, and how much we can reduce the transistor size? Okay, so we started from 10 micron to 0.25 micron. Up to this point, people were used the technique called micron technology. These are called micron technology. But from 0.25 micron, that means 250 micron technology, 250 micron. So from 180 nanometers, so from this one onwards, we have 180 nanometer technology. So nowadays the people are using 22 nanometer technology. Okay. So beyond the 22 nanometer technology, another field effect transistors came into existence that is called FinFETs. After 22 nanometer, FinFETs came into existence. Okay, so till of course nowadays the ICs are also from 22 nanometer technology only. Sometimes they are going for the beyond that level also, but this is the scaling of the transistors can be possible. That means process generations are possible from microns to nanometers are possible. So the manufacturer will give you the new process generation from so new process generation for every 2 to 3 years. So they will change the new process generation for every 2 to 3 years. That means they are able to scale down the device from for every 2 years, so that they are able to make the transistors at that particular technology node, and they can make an ICs from that one. For example, 32 nanometer technology. For example, if I'm saying the 32 nanometer technology, that means the length of the transistor will be 32 nanometer. Okay, so therefore later people will realize that they are able to achieve the 22 nanometer also. They are possible to reduce the length by 22 nanometer. So that like this, the manufacturing industry will come forward. If you're reducing the transistor size from one level to another level, the manufacturing industry also take that information, and they can make the manufacturing devices in order to make the ICs according to that particular level. So with this, we have come to the end of the session. And of course, I want to discuss about the module test related information. I put it in the Moodles. You please go through it once. Okay. Each and every concept is there. And what is the first chapter says that, second chapter says that, all these things we'll discuss about it. Okay. Okay, with this, we stop here today, and we see remaining things in the next class. If you have any doubt, please send me the personal messages. I will respond to that one, or to my mail also. Okay. Please don't hesitate to ask me the questions. Thank you. Yes, you can leave.